All right, so this is like the 5th time trying to record this video. I don't know why I had no audio in the last one. I don't understand what I'm doing wrong or if I'm even doing anything wrong. Anyways, I'm going to try to move a little bit quicker though through this. So if you already watched the video and you just needed to skip through and maybe listen to how I'm explaining certain problems, then go ahead and do that. But I figured, you know, just in case, here you guys go. So I'm sorry about the other one. All right, anyways, okay, so I have my table of values ready to go, and we have a closed interval, and what do the instructions say? It says use analytic methods to find the extreme values of the function on the interval and where they occur. Okay, so we're finding the extreme values. We have a closed interval, so we have 0.5 to 4. I'll leave some space because I don't know what critical values we're going to find in between that interval. Okay, and then we're going to need to take the derivative. All right, so let's go ahead and do that. So f prime of x. Now it helps, we're going to have to use, you know, special things for the natural log of x, and then 1 over x is the same as x to the negative 1 power because we'll have to use power rule on that. So the derivative of x to the negative first is a negative 1x, and then I have to subtract 1 from that one. So negative 1 minus 1 is minus 2. Plus the natural log of x, that's one of those special exponential derivatives that we learned in, I think, 3.9. And that would be 1 over x. If you forgot, make sure that you put those in index cards like I told you to. These ones you need to try to remember. Natural log of x and e to the x are like the easiest ones to remember out of the list that you were given. I think there was like 6. Okay, so we have this, and then to figure out where the critical values are, we need to set that derivative equal to 0. So 0 equals, and I'll just write this as negative 1 over x squared because we have to drop that like it's hot, plus 1 over x. Okay, and all right, so we need to solve for x, and we need to get x out of the denominator. So let's go ahead and fix that real quick. So remember, we can get anything out of the denominator we want. So I want to get rid of the x squared since it's the biggest. So I'm going to multiply by x squared because I know that those will cancel. But whatever I do to one term, got to do to all. Okay, so that's 0 equals negative 1 plus this x reduces out. We have 1x. And now it's super easy to solve. Add 1 to both sides, and we'll get 1 equals x. Okay. Now, I do know that there is a restriction there. X, like up here, cannot equal 0, because then it's undefined. But 0 is not in my interval, so I don't even need to worry about it. So if you were wondering why I didn't mention that, that was why. Okay. All right, so I have a critical value of x equals 1 that I can put in my chart. And we'll need to find those f of x values, the y values, okay? And so let's go ahead and do that. If I plug in a 0.5 for x, 1 divided by 1/2 is what, 2? And then 2 plus the natural log of 0.5. So I just want to find the decimal. Let's do that. So 2 plus the natural log of 0.5 is 1.307. Okay, if I plug in a 1, 1 over 1 is 1. The natural log of 1 is 0, so 1 plus 0 is 1. And then 4, 1 over 4 is 1/4. 1/4 plus the natural log of 4. So 1/4 is the same as 0.25, right? Plus natural log of 4, 1.636 approximately. Okay, so we need to see what's going on here. This is an exponential graph because we have the 1 over x and the natural log, but I don't know what this looks like. So I'm going to take it to the graphing calculator to kind of help me on what this graph is going to look like. Okay, and so y equals, and I'm going to type in parentheses 1 over x plus the natural log of x, and I want to change my window. The interval is 0.5 to 4. So that's what I'm going to set my window is, and then graph it. to zoom out a little bit. I want to see more of the graph. Okay, yeah, that definitely looks exponential. All right, so since I know that this is what's happening on this graph, from 0.5, let me go back to the interval. Means at 0.5 we're up above, and then 1, 2, 3, 4, we're a little bit lower, pretty much. Okay, that's what this is showing. It's almost like a straight line, but it's not. Okay, so we only have an absolute max and an absolute min. Okay, so my absolute, actually this part is higher. This side's higher. So my absolute max is on this side. My absolute min is on this side. Let me zoom out again. Sometimes I have to play with the zoom. Come on. Why are you taking forever? All right, I changed my window from 0 to 4 instead of 0.5 to 4. And now that looks a lot better. So I had to pause it and then be like, okay, I need to figure this out. So sometimes you have to mess with the window and the zoom to get a good picture. But yeah, it does go from low to high. So my picture's a little bit off. So I'm going to cross off that point and make it a little bit higher to show that it went, you know, down and then low and then it goes up. Kind of like a chair. Makes me think of like a car seat, car chair. All right, so this one is my absolute max and that's my absolute min, plus it's bigger, right? And obviously at 1, 1, it's just like there's no highs and lows, there's no dips or curves or anything, it's just exponential. So there isn't really anything going on at x equals 1. All right, so we have an absolute max of 1.636 at x equals 4. And we have an absolute min of 1.307 at x equals 0.5. Got to try to move through these problems a little bit quicker, but I want to explain everything. Ah! All right, now number 12, same thing, but we have g of x equals e to the negative x power. I have my t-chart ready. I'm going to go ahead and take the derivative. The derivative of e to the x is itself, but we have to do the derivative of the exponent when it's something different than just an x. It's a negative x, and the derivative of negative x is a negative 1. So negative 1 e to the negative x. And then we set that equal to 0. And then you have to isolate the e to the negative x. You have to divide both sides by negative 1. 0 divided by anything is 0. And then we have this. Here's the thing, though. E will never be 0. Okay, so that means that x cannot equal 0 here, so that means that the derivative does not exist. But that means that 0 is a critical value, because there might be a high or a low there, a max or a min. Okay, so let's take a look at this. All right, and did I want to graph it? Yeah, let's graph it. So when I graph it, this is e to the negative x. We don't have any max or mins in between. There's just the absolute max on the left and the absolute min on the right. Okay, so we have an absolute max of, I need to figure out what they are. That's the part I haven't done yet, Mrs. Garcia. All right, e to the negative x power, so e to the negative times negative 1 power pretty much. Well, that's just e to the 1, and e to the 1 is approximately 2.7. Okay, e to the 0 is just 1, but like we saw on the graph, it doesn't mean anything because it's not a max or a min. Okay, and then if we plug in a 1, e to the negative 1 is approximately 0.37 if you type that into your calculator. All right, so our absolute max is a 2.7 at x equals negative 1. And we have an absolute min of 0.37 at x equals positive 1. Alrighty, next one. All right, h of x equals the natural log of x plus 1. I have the table ready. Let's just take our derivative. Okay, so the derivative of natural log is 1 over the input, so that would be 1 over x plus 1. Okay, and automatically we already should be able to see that there is a value that x cannot equal, because it'll make the denominator 0, so we have a restriction. That means there is going to be a spot where the derivative does not exist, and that is at x equals negative 1. If x equals negative 1, it makes the denominator 0, so it's going to be restricted there, okay? But that means negative 1 is a critical value to try. But here's the thing. Is negative 1 in this interval? No, not in interval. So then I don't even need to figure out what it is because it's not even in the interval from 0 to 3. So we're good. All right, let's go ahead and solve this. So set it equal to 0 because you always set the derivative equal to 0 to find the critical values. Okay, basically where it crosses the x-axis at on the derivative graph. Okay, so I need to solve for x, so we need to multiply by x plus 1, both sides. Now, when we do that, it cancels out here, and 0 times anything is 0. But 0 does not equal 1. So there are no critical values in the middle. We just have the endpoints. So we're just going to have a max and a min, an absolute max and an absolute min because we have a closed interval. All right, so if I plug in a 0, natural log of 0 plus 1, that's the natural log of 1. But the natural log of 1 is 0. If I plug in a 3, 3 plus 1 is 4, so I'll have the natural log of 4, and that is approximately 1.39. Okay, so here's my max, 1.39, and the min at 0. So we have an absolute max of 1.39 at x equals 3. We have an absolute min of 0 at x equals 0. Well, I was highlighting answers and then I forgot. Guess that'll just be the same color. All right, that was 13. All right, number 14, we have k of x equals e to the negative x squared, and the interval is from negative infinity to positive infinity, so this is an open interval and it goes on forever. Okay. So let's just start by taking a derivative. So k prime of x equals, we have to do chain rule, so derivative of the exponent there. So derivative of negative x squared is a negative 2x, and then the derivative of e to the x is just e to the x, and whatever's in the exponent, so negative x squared. All right, and we should notice something here, that we have two quantities being multiplied together. I like to put parentheses around it to kind of show those two quantities. So let's set this equal to 0. And then we can break apart those factors and set them each equal to 0. So we'll have negative 2x equals 0 and e to the negative x squared equals 0. I'm going to start with the e to the negative x squared because that's never going to be 0. So never. And then if I divide both sides by negative 2, x equals 0. So I have a critical value, and that is the only critical value that I can try, a 0. So e to the negative 0 squared is just e to the 0, but anything to the 0 power is 1, okay? So, but we don't know if this is a maximum or a minimum. So this is where we're going to need to do a sign chart or number line because we don't know. Now we could also graph it and look at it too. All right, so let's pick a number less than 0, such as a negative 1. If x is a negative 1, oh, sorry, it has to go into the derivative. This is, we're talking about the slopes. Okay, so that's going to tell us max or min. So if we plug in a negative 1 for x, negative 2 times negative 1 is a positive 2. And then this will always be a positive number. So we have a positive times a positive, so this is positive. If I plug in a positive 1, negative 2 times 1 is a negative 2. And then e to no matter what number is still going to be a positive number. So we have a negative times positive is negative. Okay, so I know the slopes go from positive to negative, so then I know that it must go up and then down. So that means we have a maximum at 0. Okay, so this is a max. Now, because we have an open interval, it's not an absolute max. It's open, so it's just called a max. So we'll call it max of the value is a 1 at x equals 0. I totally missed that. All right, now for this one, we have f of x equals sine of x plus pi over 4 on the interval from 0 to 7 pi over 4. So to kind of give us a frame of reference on what that interval looks like, remember we're talking about the unit circle. So we know that this is 0, and then this is pi over 2, pi, 3 pi over 2, 2 pi. I'm not going to put all of them on here. But since these are increments of pi over 4, we know that this is pi over 4. This is 3 pi over 4, 5 pi over 4, and then 7 pi over 4. So it's going from 0 to 7 pi over 4. So that means we're starting at 0 and we're going all the way around until here. So we're just missing that last little piece of the pie. Okay, so that kind of helps know how far we can go as far as critical values go. Okay, and we're dealing with a trig function, so we have to remember our trig values like sine, cosine, tangent, the basic ones, pretty much, for the most part. All right, so we have f of x equals sine of x plus pi over 4. We need to take a derivative. All right, when we take a derivative, we have to do chain rule because we have a function within a function. And the derivative of x is just a 1, though, and the derivative of pi over 4 is 0 because it's a constant. So it's just 1. And then the derivative of sine is cosine, and then you keep the stuff inside. Okay, and then remember we set this equal to 0. All right, and then we have to figure out, well, what x values would we plug in and add to pi over 4 make the cosine 0? Well, where on the unit circle is the cosine 0? Well, the cosine is 0 at pi over 2 because that's the point 0, 1. Cosine is the x value, sine is the y value. And cosine is also 0 at 3 pi over 2 because that's 0, negative 1. The cosine is 0 there. Those are the only two spots. So we need pi over 4 to add to something to either equal pi over 2 and 3 pi over 2. Okay, well, to equal pi over 2, if we have pi over 4 plus pi over 4, that would be 2 pi over 4, and that reduces to pi over 2. So that means that x would need to be pi over 4. But what do we need to add to pi over 4 to get 3 pi over 2? Well, let's try different ones. We tried a pi over 4. What about 2 pi over 4? 2 pi over 4 plus 1 pi over 4 would be 3 pi over 4. Nope, I need this one. Try 4 pi over 4. Wait, is that what I want? I tried 1 pi over 4, 2 pi over 4, 3 pi over 4. If I add a 3 pi over 4 plus pi over 4, that would be 4 pi over 4. That would be just 1 pi. Not far enough. All right, add, I did 3, do 4. 4 pi over 4. 4 pi over 4 plus pi over 4 is 5 pi over 4. Nope, not close enough yet. Try a 5 pi over 4. 5 pi over 4 plus pi over 4 is 6 pi over 4, and that reduces to 3 pi over 2. So x also needs to be 5 pi over 4 because when we add that to pi over 4, it equals 3 pi over 2. And that is another spot on the unit circle in that interval where the cosine will be 0. Okay, so these are my critical values that I need to add to my table. So I need a pi over 4, so obviously it's smaller, and then 5 pi over 4. Okay, and we're going to plug those in to the OG, but before I do that, let's do, while we have the derivative right here, let's go ahead and do a sine number line. So we have 1, 2, 3, 4 values to have. We have 0, pi over 4, 5 pi over 4, and 7 pi over 4. Okay? And, okay, so I want to know what's happening at 0 because we're including 0. I can't go lower than 0 because that's out of my interval. So at 0, if I were to plug in a 0 for x here, because this is the derivative graph, f prime of x right here, 0 plus pi over 4 is pi over 4. Cosine of pi over 4, well, remember that's square root of 2 over 2, square root of 2 over 2. So the cosine is square root of 2 over 2. Well, both cosine and sine are, and that's a positive number. So we're positive exactly at 0, okay? And then, yeah, remember this is a cosine graph. And then at pi over 4, I need something in between pi over 4, so maybe like, I don't know, pi over 6. Okay, because that would be before a pi over 4. So it goes pi over 6, pi over 4, pi over 3, and then pi over 2. So if I plug that in, pi over 6 plus pi over 4, well, I don't want to figure that out, so I'm just going to use the calculator. I don't want to do fraction math in my head right now. I want to do things quickly, and so that's what the calculator is for, right? So I need to add pi over 6 plus pi over 4 in the cosine. So I'm just going to do this, parentheses, second pi over 6 plus parentheses, second pi over 4, and I get a positive number. Okay, and then between pi over 4 and 5 pi over 4, well, pi over 4 and 5 pi over 4, I could pick anything in between here. So let's pick, what, pi? Pi sounds good. Pi's in there. Apple pie sounds good. All right, so that would be cosine of pi plus pi over 4. Cosine of pi plus parentheses pi divided by 4. Negative 0.707. Okay. So I know from here to here, I'm going positive, negative, so I know that that's going to be a max. From here to here, it goes positive, positive, so that tells me that it's just climbing. Positive, positive. All right, and then from, let's see, 5 pi over 4 to 7 pi over 4, I need to pick something in between here. So 3 pi over 2 is in between there. So plug that in, cosine of 3 pi over 2 plus pi over 4. 3 pi over 2 plus parentheses pi over 4. Aren't you guys thankful for calculators? Positive 0.707. So it's positive. So it goes from negative to positive. So at 5 pi over 4, we know that it's doing this number, and that's a minimum. Okay. And then at 7 pi over 4, since we can include 7 pi over 4, at 7 pi over 4, if I were to add that, 7 pi over 4 plus pi over 4 is 8 pi over 4. 8 pi over 4 reduces to, 8 divided by 4 is 2, so 2 pi. So, oh, well, that's easy. Cosine of 2 pi, that's the 0.10. So it's just 1. So it's positive right at 7 pi over 4. So that means it's going to be increasing to there. Okay, so on the very left end, we have a minimum because that's the low point there. On the very right end, it ends on the top there, so it's a maximum. Okay, and then we have a max and a min here. Okay, so we have an absolute min and an absolute max because that's the lowest low and the highest high. And then these are our local max and mins in between. Okay, so let's look at what these values are by plugging them in, plug and chug. Okay, if I plug in a 0, and this is where we go to the OG now, 0 plus pi over 4 is pi over 4. Sine of pi over 4 is square root of 2 over 2. And what is that as a decimal? Second square root of 2 divided by 2 is 0.707. Oh, should have known that. So I'm just going to put 0.71. Okay. Pi over 4 plus pi over 4 is 2 pi over 4, which reduces to pi over 2. The sine of pi over 2 is 1. 5 pi over 4 plus 1 pi over 4 is 6 pi over 4. That reduces to 3 pi over 2, and sine of 3 pi over 2 is 0. Oh, I'm sorry, not 0. That's cosine. The negative 1. And then plug in a 7 pi over 4 plus pi over 4 is 8 pi over 4, which reduces to 2 pi. Sine of 2 pi, the y value is 0. All right, so we have our absolute minimum, because that's the lowest. Absolute maximum, because that's the highest. Okay, and then we have a local minimum right here, or right here, and a local max. Okay, so here we go. Absolute max, the biggest one is positive 1 at x equals pi over 4. We have an absolute minimum of the lowest is negative 1, the lowest low, at x equals 5 pi over 4. And then the other two are the local maximum. So the local max was at pi over 4, so at 1. So we have a local max of 0. Wait. Yeah, it was 0. I don't know why I second guessed myself. 0 at, because the other maximum is right here, 7 pi over 4. At x equals 7 pi over 4. I'm trying to do it too fast. That's why I'm confusing myself. And the local minimum of 0.71 at x equals 0. So this one had a bunch of them. A bunch of extrema. Keep knocking the camera. Sorry about that. Earthquake. Just kidding. All right, number 16, g of x equals the secant of x on the open interval from negative pi over 2 to 3 pi over 2. And I have my table of values ready. I already took the derivative of g of x. So g of x equals secant of x. Its derivative is secant x tangent x. And I kind of want to see what the unit circle, I need a picture. We know our interval is from, so this would be our negative pi over 2. It's the same thing as 3 pi over 2. But we're going all the way around, always go counterclockwise, but then it goes to 3 pi over 2, which is the same thing. So it's making a full circle. It's just starting at negative pi over 2. And we'll see what that looks like on the graph, because we are going to need to graph this one. A graph is a really good visual for our anytime we have a sine, cosine, secant, cosecant, any of those graphs. Tangent, cotangent, any of those. All right, so let's finish our derivative problem. So let's set this equal to 0. And I have two separate functions there, secant of x times tangent of x. And we can break those apart and set them each individually equal to 0. Okay, and we need to figure out when are these going to be equal to 0. Well, secant is a tricky fella because secant is the reciprocal of cosine. It's 1 over cosine. But cosine can't ever be 0 then, because then it's in the denominator. It would make it undefined. So this one will never be 0. Okay, so I'm stuck there. I don't get any critical value out of that one. Tangent, though, can be 0. Okay, tangent is actually going to have a couple of spots where we're going to get it to be 0 on this interval because it's the whole circle. So we have to remember that tangent is the same as sine over cosine. So it can equal 0, but no matter what, the cosine can't be 0 because we can't have 0 in the denominator. Okay, so we have to be careful about that. So where on the unit circle would we have zeros and it's not the x value but just the y value that is 0? Well, that's at these points. X is 1, y is 0. X is negative 1, y is 0. So 0 radians and pi radians, pretty much. Okay, so 0 and pi. So, because if I have sine over cosine, 0 divided by negative 1 is 0. 0 divided by positive 1 is 0. So when x is 0, the tangent of x will be 0. When x equals pi, the tangent of pi will equal 0. So those are two spots, 2 critical values that we are getting from tangent of x. Okay, so let's add those to our table. So 0 and pi. I got a little crazy there. All right, and let's also remember some things about what the graph of secant looks like. So graph of secant up here. Remember, it's the reciprocal of cosine. So we have to flip the waves. We draw the cosine graph and then we flip the waves. Okay, so let's go ahead and draw the cosine graph and see what the heck is going on here. So I'm going to draw it. Draw with me. My interval is from negative pi over 2 to 3 pi over 2. So 0, pi over 2, and then pi, 3 pi over 2. Remember, this is how we increment it. Let this be 1, this be negative 1. Okay, so when we draw the secant graph, we start with cosine, okay? And cosine starts up at 0, 1. And then it goes down, down, up, up, down, down, up, up. And then if we continue this way, it would be down. Okay, so there is my cosine graph. And just for reference, let's write cosine of x on there so that we know that's cosine, not secant. Now, secant, if you remember from last year, we need the vertical asymptotes at all the x values, at all the zeros. So at negative pi over 2, I have an asymptote. At pi over 2, there's an asymptote. And at 3 pi over 2, there's an asymptote. And then we flip the waves. So this would be the vertex, flip the wave. So all the green is secant. So when you graph secant of x, you only see this. Watch. I haven't ever done it here, so I'm assuming that that's what it can... Oh, secant of x is same as 1 over cosine. And I need to change the window. Negative pi over 2 to 3 pi over 2. See, this is all secant is going to show. The parabola is the green. Isn't that so cool? So cool. I love it. Okay, so we only have a local maximum and a local minimum because this is an open interval, okay? And if, notice, at negative pi over 2, it's undefined. There's an asymptote there. So we're undefined there, plus we can't include it anyway because it's not included on the interval. And we also have a vertical asymptote at 3 pi over 2, so that's also undefined. Okay, so it's very clear, though, we only have a 1 minimum and 1 maximum. Okay, and look, the minimum happens to be higher up than the maximum. That's okay, sometimes that happens. So we have a minimum when x is 0, the y value is 1, so 0, 1. We have a maximum when x is pi, y is negative 1. Okay, so we have our local max and min. So I'm going to mark this on my graph here. It's a min, that's a max. Okay, so our answer is we have a local max of, it was at negative 1 at x equals pi. And we have a local min of positive 1 at x equals 0. And that's number 16. All right, number 17, f of x equals x to the 2/5 on a half-closed, half-open interval from negative 3 to 1. Closed on the negative 3, open on the 1. And we have to use power rule to take the derivative of f of x. So that would be 2/5 x to the 2/5 minus 1. So 2/5 minus 5/5 is a negative 3/5. And let's rewrite that and set it equal to 0 all in one step. So that would be 2/5, and then we have to drop this like it's hot, and let's convert it to a radical. That is a 5th root of x cubed, x to the 3/5. Okay, so here's the thing. We have x in the denominator, so that means that x cannot equal 0 because it will make the denominator 0, which is undefined. Okay, so that means the derivative does not exist at x equals 0. This is never 0. But because the derivative does not exist there, that is a critical value. We get to add to our table. Okay. So also another thing to take note of is that -3 and 0 are included in the interval, but 1 cannot be included because it's not in the interval. So not in interval. So I'm not even going to figure out what it is because it doesn't even matter. Okay. So obviously whatever one is the biggest one is the max, whatever one is the smallest one is the min. So I don't even need to do a sign chart because I only have two options. One's bigger than the other. One's going to be the max, one's going to be the min. Okay. Okay. And we can also verify that on the graph as well, which we will. Okay, so if I plug in a -3, and when I plug it in, I prefer to look at it like this in radical form. That just processes in my brain a little bit easier. I don't know about you guys. So if I plug in a -3, -3 squared is 9. This is the 5th root of 9, okay, which is approximately, when you type it into your calculator, 1.155. If I plug in a 0, that's easy. 5th root of 0 is 0. Easy peasy, okay? So obviously we should know what our max and min are because whatever one is bigger is the max versus the min. But let's take a look at the graph. This is x to the 2/5 power. And the window is from -3 to 1. Let's graph. Okay. So we can see that there's something undefined that's happening right here, that vertical line. And at -3, there's our maximum. And at 0, there is our minimum. Okay? Because it does go down there and reach a low. How low can you go? So we have a max of 1.55. at x equals -3, and a min of 0 at x equals 0. Easy peasy. All right, number 18, we have f of x equals x to the 3/5. I already have the derivative done. We just need to set that equal to 0 and look for some critical values. We have a half open interval, open on the -2, closed on the 3. So 0 equals, this is 3/5, and then x to the -2/5, we got to drop it like it's hot to change that exponent to a positive, and that is a 5th root of x squared. So again, we run into the same thing as the last problem. X cannot equal 0 because that would make the denominator undefined. So that means that the derivative does not exist at x equals 0, and this is never going to be equal to 0. And we saw that on the graph in the last one. There's something strange going on that makes it not continuous. It just doesn't work, okay? But it still gives us a max or a min, okay? So 0, again, is the value that we're going to use. That's our critical value in between. Now, if I plug in a -2 for x, and like I said, this is a 5th root of x cubed. -2 cubed, the 5th root of -2 cubed, or in other words, 5th root of -8, it doesn't even matter what that is because it's not included in the interval. So not in interval. If I plug in a 0, 5th root of 0 is 0. Plug in a 3, 5th root of 3 to the 3rd, that would be 5th root of 27. That I need to figure out in the calculator. So I need math 5, 5th root of 27 is 1.933, approximately. Okay. And I need to see what this looks like in the graph, though. So I'm going to go ahead and graph it. So y equals x to excuse me, to the 3/5 power. And let's change the window. The interval is from -2 to +3, graph. Okay, I see why x can't equal 0. There's a vertical tangent right there, like a shelf, so we can't do anything about that. So our minimum, actually we don't have a minimum because it's from, it would be on this side, but because we don't include that, we can't count it as a minimum. So our maximum is only on this side, and x can't equal 0. So we only have a maximum. So we have a max of 1.933 at x equals 3. That was easy enough. All right, on to the next two. All right, number 45, if f of c is a local maximum of a continuous function f on an open interval from a to b, then f prime of c equals 0. Well, it's missing something. We set the derivative equal to 0, but we also look for where the derivative does not exist when we're set equal to 0. Okay, so it's missing part of it. So this is false. So we can say the max f of c could occur at a place f prime of x does not exist. Like a corner. It could be a maximum there, but it doesn't have a derivative that exists there because it's a corner. So there's a possibility. All right, so number 46, if m is a local minimum, lowercase m, and capital M is a local maximum of a continuous function f on AB, an open interval, then lowercase m is less than uppercase m. Justify true or false. Well, if we look at number 16, we had a local maximum that had a lower y value than the local minimum. So just because it's a minimum doesn't necessarily mean it's going to have a smaller value than the maximum. So this is false. And so to justify that, just draw a picture. Like we can have a maximum down here and then a minimum up there. So we could have a max down here and a minimum up here. And obviously the minimum is higher than the maximum, so it could happen. And our picture will do enough to justify in this case. And that's it. I hope this video works. It better work.